Manish? Manish? Yes, sir. Sachin?
Yes, sir.
Yeah, can you define noise?
Sir, noise is unwanted signal, sir.
Okay, that is fine. It is an unwanted signal. How does it will affect the performance of a communication system?
So it might be like
Hmm.
when we use diodes in the signal,
Ah,
and due to some noise, there may be some fluctuations and also.
okay. Yes, sir. Sai Ram.
Yes, sir.
Ram Sai. Yeah, can you
Sir.
define what are the sources of noise? Different sources of noise, man. I said broadly two categories. Can you just mention what are
External and
the?
internal.
Yeah, one is
External,
external to the system,
internal,
and
internal.
another one is internal to the system, right?
Yes,
So
sir.
external to the system is what I said. It is due to atmospheric noise, galactic noise, and all, right?
Yes, sir.
Uh, yeah, just to have a recap. So I discussed yesterday. I defined what is noise, right? I said it is an unwanted wave and it will be disturbing the transmission and processing of the signals in the communication system, right? Then I said about the sources of noise. So basically, there are two sources we say. One is external to the system and another one is internal to the system, right? The external to the system is what it is due to atmospheric noise, we say galactic noise or man-made noise, right? Another one is the internal to the system. I said it arises due to the spontaneous fluctuations of currents or voltages in the electrical circuits, right? And this noise that is internal to the system is the basic limitations on the transmission or detection of the signal in the communication system, right? And as an example, I said this spontaneous fluctuations of currents and voltages in the electrical circuits is the short noise and the thermal noise. So I defined what is a short noise. Mm, yes, Karunya, can you say what is short noise?
So it is
Karunya.
due to discrete current flow.
Yeah, so short noise arises due to the discrete nature of the current flow in the electronic devices like diodes and transistors, right? So as an example, I gave a photodetector circuit. It will be generating the current pulse, right? Every time the electron is emitted from the cathode. So when the electron will emit from the cathode, whenever a light falls on the cathode, so the cathode will emit the light. Cathode will emit the electron, so that electron will be coming in the form of pulse, current pulse, right? So as I said, the electrons which are naturally emitted or at random times will be denoted by tau suffix k, where the value of k can extend from minus infinity to infinity. And here we have assumed that the random emissions of the electrons will be going on for the long time. So we can model the total current flowing through the photodetector circuit may be modeled as an infinite sum of the current pulses. So with that, we can express x of t as the random process, which is equal to what? Summation from k equal to minus infinity h of t minus tau k, right? This h of t minus tau k is known as the current pulse generated at time tau k, right? This process x of t sorry, is a stationary process and we call this as a short noise. And I told what is the mean of the short noise and what is the autocorrelation and other things, right? So we make this as a Poisson process, and I said the mean of this short noise will be mu suffix x is denoted as mean, right? It is lambda into integral from minus infinity h of t into dt, right? So lambda is the rate of the process and h of t is the waveform of the current pulse, and this is the autocovariance function of that process, which is defined as Cx of tau, which is equal to lambda into integral from minus into infinity h of t into h of t plus tau into dt, right? And then I said what is the autocovariance function, so which is equal to what? Means if I assume that current pulse has a rectangular pulse, right, of amplitude a and duration t, right, then the mean of the short noise process will be what? Lambda into at, and its autocovariance will be denoted as cx of tau, which is equal to lambda into a square of t minus capital tau, t minus tau over the interval when tau is less than t, and it is 0 when tau is greater than t. Right? It is like a triangular waveform. Then I said thermal noise, right? So thermal noise is due to the random motion of the electrons in the conductor, right? And how do we find the mean square value of this thermal noise? Is denoted as V suffix Tn, right, which appears across the resistor and which is measured in a bandwidth of delta f hertz, will be given as this. So there is a mean, right? As mean square value. So E of V square Tn is equal to 4 kTr into delta f whole square. Even this delta f, instead of delta f in some textbook, they will be written as B as the bandwidth. Okay, we can write that also. As I said, K is the Boltzmann constant, T is the absolute temperature, which is measured in degree kelvins, and R is the resistance. Fine. Then we have discussed how we can model this noisy register by using Thevenin's equivalent circuit and as well as the Norton's circuit, right? So we can represent this noise voltage generator having a mean square value of E of V square Tn, right, in series with the noiseless resistor. So this is the Thevenin equivalent circuit for that noisy resistor, right? And this one is the Norton equivalent circuit. So in case of Norton, we write the current source, okay, the noise current generator, which is what? E of I square Tn. So parallel to this, there will be a conductance, okay, so which is equal to 1 by R, we say. Okay, so how do we model this noisy resistor? Is this by using Thevenin's and as well as Norton's. Yeah, so we know how to write for current, right? So E of I square Tn is equal to, I said, 1 by R squared into E of V square Tn. So just I substitute the value of E of V square Tn as 4 kTr delta F. So 1 RR will get cancelled. So 1 by R will be G. So it will be expressed as 4 kT G delta F into M square. Okay, then as I said in the noise calculations, we use the transfer of power, that is maximum transfer theorem, right? As I said, the maximum power transfer theorem, what it says, the maximum power will be transferred from source to the load when the source resistance is equal to the load resistance, right? So that is what is written here. And here what we are saying is when the power produced by the source is divided equally between the internal resistance of the source and the load resistance, then the power delivered to the load is known as the available power. So this is a catchy point which we need to remember and understand. What is that available power? What is that available power? We say when the power produced by the source is divided equally between the internal resistance of the source and the load resistance, then the power delivered to the load is known as the available power. Okay, so with respect to this, the for the noisy resistor, okay, that produces an available noise power which is equal to 4, and that which is equal to kT delta F watts. It can also be written as kTB, where if I say B is delta F, there is a bandwidth. Okay, kTB is the available noise power. This should be registered in your mind. Then I was discussing about the white noise, right? As I said, this white noise will be having a power spectral density of what? N0 by 2, and it is independent of the frequency, because this white light contains all, means equal amount of all frequencies, right, within the visible band of the electromagnetic radiation. With respect to that, we call this as a white noise. So how do we draw the spectrum? That is, power spectral density is this. So this is the power spectral density of the white noise, right? So which is equal to constant for all frequencies, and its value is n0/2. I will tell what is n0. Okay, and we know how to find the autocorrelation function, right? The inverse Fourier transform of the power spectral density will give you the autocorrelation function. If I take the inverse Fourier transform of this, I will get the impulse function, okay, having a value of n0/2, right, into z delta function. So this is the autocorrelation function of the white noise. So as I said, n0, its dimensions will be what? Watts per hertz. Okay, so n0 is reference to the input stage of the receiver of the communication system, and it will be defined as n0 is equal to k into TE, where k is the Boltzmann constant and T suffix E is the equivalent noise temperature of the receiver. So T suffix E is the equivalent noise temperature. Okay, so how do we define this equivalent noise temperature? The equivalent noise temperature of the system is defined as the temperature at which a noisy register has to be maintained, such that by connecting the register to the input of a noiseless version of the system, so it produces the same available noise power at the output of the system as that produced by all the sources of the noise in the actual system. So this is how the definition of the equivalent noise temperature. I repeat once again, the equivalent noise temperature of a system is defined as the temperature at which a noisy register has to be maintained, such that by connecting the register to the input of a noiseless version of the system, okay, it produces the same available noise power at the output of the system as it produced by all the source of the noise in the actual system. So that is how we define the equivalent noise temperature. So what is the available noise power? Just now I said available noise power will be equal to KT into delta F, or it is also known as KT into B. Okay, so N0 will be equal to what? K into T. K is the Boltzmann constant, I said. T is the equivalent noise temperature. So what is the important feature of the equivalent noise temperature? Is that it depends only on the parameters of the system. Okay, that is the one important feature of the equivalent noise temperature. Yes, is this clear? Equivalent noise temperature of a system, how do we define? Is the temperature at which a noisy register has to be maintained, such that by connecting the register to the input of a noiseless version of the system, it produces the same available noise power at the output of the system as that produced by all the sources of the noise in the actual system. Okay, this is how we define the equivalent noise temperature. Okay, so already I said about this, and I have shown the diagram also. The autocorrelation function is the what? Inverse Fourier transform of the power spectral density, right? So I have shown the diagram of power spectral density of white noise and as well as the autocorrelation function of the white noise. Right? This is the power spectral density of white noise, and I said this is the autocorrelation function of the white noise. Means how do I get this one? By taking the inverse Fourier transform of this, I get the autocorrelation function. Yeah, that is why we wrote RW of tau is equal to N0/2 into and delta of tau, right? So you can write prior to this one equation as per the definition of inverse Fourier transform. What we write? Integral from minus infinity to plus infinity, right? S W of f into e power j 2 pi f tau into d tau, right? So we can take N0/2 means Sn of f or Sw of f, that is the for spectral density of the white noise, no, which is equal to n naught by 2, I said. So if I take that outside, then integral from minus to infinity e power j 2 pi f tau into df will be equal to delta tau. So that is what is written here. Okay. So the autocorrelation function of the white noise consists of what? We say delta function weighted by the factor of n naught by 2 and occurring at tau is equal to 0, right? And the autocorrelation function will be 0 for tau is not equal to 0, right? So I think here only with respect to this one you can say, right? When tau equal to 0, its value is n naught by 2 into del of tau. That is the autocorrelation function of the white noise. When tau is not equal to 0, it will be 0, right? So RW of tau will be 0 when tau is not equal to 0. Yeah. So with respect to that, then if we take any two different samples of the white noise, so no matter how closely together in time they are taken, say they are uncorrelated. Okay. So if the white noise is also a Gaussian, then the two samples are statistically independent, we say. I think this I said in the previous class also, what is Gaussian and what is its approximation of the Gaussian curve, right? And how do we approximate this white noise as a Gaussian noise? Okay, to say that the white Gaussian noise represents the randomness. Okay. Strictly speaking, we say white noise has infinite average power. Okay, and as such, it is not physically realizable because you might have observed, so it is constant value having n naught by 2 or all the frequencies, right? So if you find the average power of that, it will be infinite. So which cannot be realizable physically. So how do we then find the utility of this white noise? Okay, so the utility of the white noise process is parallel to that of the impulse function, right? Or we say delta function in the analysis of the linear system. So how do we find the effect of the impulse function? So we can find the effect of an impulse function only after it has been passed through the system, right, with a finite bandwidth. So similar to that, we can find the effect of the white noise, right, only after passing that white noise through a similar system. Okay. Therefore, so as long as the bandwidth of the noise process at the input of a system is appreciably larger than that of the system itself, then we can model the noise process as the white noise. Okay. So we take any linear system. First, we check with the delta function, right, to understand what is the impact or effect of the delta function on a system. So similar to that, we can model with respect to the white noise. Okay, to understand what is the effect of this white noise on the system. That is what the meaning of this. But to understand better, let us take some examples. So this is the first example what I have taken. That is I am passing this white Gaussian noise, which is having a zero mean and a power spectral density of n naught by 2. Okay, so that I am applying to the ideal low pass filter having a bandwidth of P and pass band amplitude response of 1. Okay, so let us try to understand what will be the output of that ideal RC low pass filter white noise, right? So I hope we will be able to visualize this. So I need to draw a ideal low pass filter, right? I am applying input to that as this white Gaussian noise having zero mean and power spectral density of n naught by 2, right? I am assuming the filter bandwidth is how much? B hertz and its amplitude response is 1. Okay, so is it possible to write from your side? How does it looks? The whatever I am saying here, the response. So I hope you're all aware of how the the frequency response of the low pass filter looks like this. Yes, I am drawing with one-sided this one. Okay, so if I take this as 0, right, and this will be B hertz. So this will be my frequency. I hope all of you have remembered this. and I said this is the amplitude response, sorry, 1. Okay, the magnitude response of 1. So this is how the frequency response of the low pass filter. Right? I have done for only for positive frequencies. It can be done for even negative frequencies also. Okay, so this is the frequency response of the ideal low pass filter, right? So for this, I am applying input as the what? White Gaussian noise with zero mean and power spectral density of n0 by 2. So let us try to understand what will be the output of that filter. Yeah, so we can write the output of the that ideal low pass filter as Sn of f, Sn of f, okay, so which is equal to, we say n0 by 2, right? So it will be n0 by 2 over what frequencies from minus b to b, okay, and it will be 0 when f is greater than b, and this is what the spectrum of that is. So this is the what spectrum of the white noise available at the output of the ideal low pass filter. Okay, so it has a value of n0 by 2 over what frequencies from minus b to b, and it will be 0 for other values of f. Yes, am I clear? Hello? Hello?
Sir.
Yeah, is this clear?
Yes, sir.
So this is the what I said, this is the output of the white noise which is available at the output of the ideal low pass filter. Okay, so this is how we express mathematically, that is Sn of f is equal to n0 by 2 over the frequencies from minus b to b, and it will be 0 for f greater than b, right? Then how do we find the autocorrelation function of the noise which is available at the output of the ideal low pass filter, right? So we have to take the inverse Fourier transform of this. Okay, if I take the inverse Fourier transform of the power spectral density of this noise available at the output of a low pass filter, I will get the autocorrelation function. Okay, so that is what is written here. Autocorrelation function of the noise, right, is the what inverse Fourier transform of the power spectral density which is appearing at the output of the low pass filter. So as for the definition, what I can write, Rn of tau, that is autocorrelation function, right, which is equal to integral from minus b to b. So this is the value of the what power spectral density of the noise, right, that is n0 by 2. Then e power j 2 pi f tau into df. So I hope here I think two more steps you can write. You take n0 by 2 as outside, then integral from minus b to b e power j 2 pi f tau into df, right? So what is the integration of that you can write? I think you people should do that and show me how do we get this as n0 b into sinc 2 b tau. So here two more steps are there, only two steps. I will give 2 minutes time to do that and show me the steps, in between steps, because I will not be able to write here. You understood now? You take this n0 by 2 outside the integration, then integral from minus b to b e power j 2 pi f tau into df, right? So what is the integration of e power j 2 pi f tau into df? Yes, I hope you all will be able to write. Hope people are doing this. Yes, what is the integration of e power j 2 pi ft into df? Yes, Aditi, can you say? Aditi. No, Aditi. What about Rishav? Yes, Rishav Kumar. No. Bharati. Yes, Bharati. No, Bharati. Anand. Anand.
Yes, sir.
ಮಾಡ್ತಾ ಇದೆಯೇನಾ? ಇಂಟಿಗ್ರೇಷನ್ ಮಾಡ್ಲಿಕ್ಕೆ ಹೇಳಿದ್ದೀನಿ, ಮಾಡ್ತಾ ಇದೀಯಾ?
ಮಾಡ್ತೇನೆ ಸರ್, ಒಂದು ನಿಮಿಷ.
What about Srujan? Srujan. No. Yes, Chandana. Chandana.
Yes, sir.
Yeah, are you doing that integration?
Yes, sir. Just a minute.
Yeah. What about Chandrika? Yes, Chandrika.
Yes, sir.
Yeah, are you doing the integration, Namita?
Yes, sir. Doing so started now.
You should be able to show that as a final result. That is whatever I have written. Okay, it requires only 2 steps. Yes, Girish.
Yes, sir.
Girish, ಮಾಡ್ತಾ ಇದೆಯೇನಾ?
Yes, sir, ಮಾಡ್ತೇನೆ.
ಸ್ಕಂದ.
ಎಸ್ ಸರ್.
ಮಾಡ್ತಾ ಇದೀನಪ್ಪ ಇಂಟಿಗ್ರೇಷನ್.
ಹಾ ಸರ್, ಮಾಡ್ತಾ ಇದೀನಿ ಸರ್.
ಲಿಯಾ. ಎಸ್, ಲಿಯಾ.
Yes, sir. I'm doing.
Yeah, are you doing the integration, ma? Are you there with me? I said I have written the expression for autocorrelation function. So in between steps, 2 steps are there. After integration, substituting limits and then bringing it to that sinc function form. So you all know what is sinc function, right? It can be defined as what? Sin pi x by pi x, right? So in that form, you need to bring it. I am asking you people to do that. Yes, Neeraj.
Yes, sir.
Neeraj.
Yes, sir.
Yeah. Are you doing it, man?
Yes, sir, I'm doing it.
Yeah. So 2 minutes over, I think. By this time, people should be able to answer or tell. Or you can switch on your camera and you can show it. Yes, Shreyas.
Yes, sir. Doing, sir.
Doing. Subiksha, Tipana.
Doing it, sir.
Doing, sir. Doing, sir.
Okay. Sanket.
Yes, sir. Trying.
What about Vishal?
Yes, sir. I'm doing it.
Still doing it. 2 steps, man. What is there? E power jx into dx is equal to what? If you treat that as x. It takes so much of time to do it. Yes, Rushank. Rushank.
Doing so.
Doing. Rishav. Rishav Kumar.
Yes, sir.
Are you doing the simplification, man?
Sir.
I expect answer from you. So what about Pooja? Pooja is not here. What about Niharika? Yes, Niharika. Why Pooja you are messaging, chatting?
Yes, sir.
Yeah, have you done that integration?
I'm doing it, sir. I'm doing it.
But still you are doing it. How much time it takes? Quickly, people should say the answer. Yes, Gautam Hegde.
Yes, sir.
ಮಾಡ್ತಿದ್ದೇನೆ integration.
ಹ್ಞೂ ಸರ್.
Yes, Akshay. Akshay Kumar.
Yes, sir. Doing it.
Integration, no, still doing. Yes, what about Sagar? Done, man? Sagar,
No, sir, I tried. I couldn't do it.
you couldn't do it. Why? What is the problem? See,
No.
e power j 2 pi f tau into df, no? I said you take n naught by 2 outside. Then what is left out in the integral? Integral from minus b to b, right? E power j 2 pi f tau into df, right? So which is equal to what I can write? E power j 2 pi f tau divided by j 2 pi f tau, na? E power j 2 pi f tau divided by j 2 pi tau, because it is integration with respect to f,
Yes, sir.
right? Yeah. So with the limits of what? Minus b to b. If I substitute those limits, then upper limit minus lower limit, right? So n naught by 2 will be there outside. Then e power j 2 pi, instead of f, I should substitute as b, right? So e power j 2 pi b tau, right? Minus e power minus j 2 pi b tau, right? Divided by j 2 pi tau will be there. I hope understanding what I'm saying.
Got it, sir.
Yeah, I hope by this time you all will be able to substitute the limits of upper limit minus lower limit, right? So now what we can do is a slight modification, that is say e power j theta minus e power minus j theta by 2j is equal to what we can write? This sin theta, right? So with that form, what I can write is n naught by 2, right, into sin 2 pi b tau divided by pi tau. Or you can take it that 2 also inside, means n naught into sin 2 pi b tau divided by 2 pi tau. Okay. So now we need to multiply and divide by b. If you do that, we'll get n naught into b into sin pi 2b tau divided by pi 2b tau. So sin pi x by pi x, I said it is sinc function, right? Sinc x. So I can write n naught b into sinc of 2b tau. I don't know, you want me to write, or I hope you people have got and be able to do it. Yes, what is your opinion? Yes, you people could do it, and I even have dictated also. Say yes or no, no. Could you do it, or you want me to repeat once again? Hello? Yes, you want me to repeat once again, or you are doing it?
We're doing it, sir.
Doing it. No, that's what I said. No, see, e power j 2 pi f tau into df will be written as what? E power j 2 pi f tau divided by j 2 pi tau, right? With limits minus b to b. Then just I said substitute the limits, right? So we can write it as what? N naught by 2. You can open the bracket. Then you can write e power j 2 pi b tau minus e power minus j 2 pi b tau divided by j 2 pi tau will be there, right? So I said we can rewrite this as n naught divided by 2 pi tau into e power j 2 pi b tau minus e power minus j 2 pi b tau divided by 2j. So this will be the thing, whatever is written in a square bracket will be in the form of sin theta. If I take theta as 2 pi b tau, okay. So I can write it as what? N naught into sin 2 pi b tau divided by 2 pi tau. Okay. So now I need to do some alteration. That is, I am multiplying and dividing by b. So if I do that, I can write it as n naught into b into sine pi 2b tau divided by pi 2b tau. And as I said, sine pi x divided by pi x will be what? Sinc x. Okay. So my x is what? 2b tau. So I can write it as n naught into b into sinc of 2b tau. So this is how we get the final expression. This one. Yes, got it? Yes, I'm asking, you could get it, or you want me to write that? Hello? Yes, Shreyas bante na? Shreyas. Yes, what about Naureen?
Got it, sir.
Got it. Yeah. Sagar bante na?
Yes, sir. There is, sir.
ಬೇರೆ ಏನು ರೆಸ್ಪಾಂಡ್ ಮಾಡ್ತಾ ಇಲ್ಲ. ವಾಟ್ ಅಬೌಟ್ ಅದರ್ಸ್? ಅಕ್ಷಯ್, ಗಾಟ್ ಇಟ್ ಮ್ಯಾನ್?
Yes, sir. Did it.
Okay, no. Shall I proceed further?
Yes, sir.
Yes, sir.
Thank you. Yeah, so yeah, this is the mathematically we can find out that the autocorrelation function of the white noise which is appearing at the output of the low pass filter as n naught b sinc of 2b tau. How do we draw that sinc function? This is what we draw. Okay, so this will be a sinc function, and it has a maximum value at tau equal to 0, so which is equal to what? N naught b. Okay, it has a maximum value of what? N naught b at tau equal to 0. Okay, then it crosses, means it has a 0 value set 1 by 2b, 1 by b, 3 by 2b, and so on. So in general, what we can say is it has it passes through 0 whenever tau is equal to plus or minus k by 2b, where k is 1, 2, 3, and so on. Okay, so this is what? This is the power spectral density of the noise which is appearing at the output of the low pass filter, and this one is the autocorrelation function. So that one only is repeated here. So I said autocorrelation function has its maximum value of how much? I said it is n naught b, right, at the origin, and it passes through 0 at tau is equal to plus or minus k by 2b, where the value of k is 1, 2, 3, and so on, right? So the input noise W of t is the Gaussian, right, and it follows that the band limited noise at the filter output is also a Gaussian. Okay, so input noise is a Gaussian, output noise is also a Gaussian, we say. So if this noise, that is we denote that as n of t, right, is sampled at the rate 2b times per second, okay, then the resulting noise samples are uncorrelated, and since they are Gaussian, they are also statistically independent. Okay, so the joint probability density function of the set of noise samples obtained in this way is equal to the product of the individual probability density functions, we say. Okay, so each such noise sample has what? A mean of 0 and a variance of n naught b. Okay, ultimately what we need to understand is what is the value of mean of that such a noise and what is its variance. It has 0 mean and variance of n naught b. Okay, so to consider the second example, I am considering in the previous example I considered an ideal low pass filter, right? So here I am considering RC low pass filter. Okay. So you all know how the RC low pass filter will looks like. So you need to draw a circuit of RC low pass filter. For that, input is the white Gaussian noise having a zero mean and a power spectral density of N0 by 2. Right? So then I'm trying to find out what is the output of that and how does it looks like. Right? So we all know the transfer function of the RC low pass filter can be written as like this: h of f equal to 1 divided by 1 plus j 2 pi f into RC. Okay, I will come back to this. This is the what? This is the expression for the power spectral density of the noise appearing at the low pass filter output. Means at the output of the low pass filter, I get the noise, and its power spectral density will be written as this: N0 by 2 divided by 1 plus 2 pi FRC whole square. I think you people are noting these equations. So this is the what? This is the transfer function of the RC low pass filter. H of f is equal to 1 divided by 1 plus j 2 pi f RC. Okay. So this is the expression what I can write for the power spectral density of the noise, right, which is appearing at the output of the RC low pass filter. Which is what? N0 by 2 divided by 1 plus 2 pi f RC whole square. I will say, how do I get this Sn of f is equal to N0 by 2, this value? Okay. Okay. So this is what I am saying. This is the RC low pass filter, right? So for this, I am applying the input as what? White noise, which I denoted as W of t, right? Which is having a zero mean and a power spectral density of N0 by 2. So output noise of the RC low pass filter, I am denoting it by N of t, right? I said the power spectral density of the noise, which is appearing at the output of this filter, will be denoted as what? Sn of f. So which is equal to what I wrote, which is N0 by 2 divided by 1 plus 2 pi f RC whole square. So how do I get this one is, so I can write Sn of f, that is the power spectral density of the noise which appears at the output of the low pass filter, right? So which is equal to, I will just write. So before writing this Sn of f, we can write it as Sn of f Sn of f will be equal to, okay, Sn of f will be equal to, which is equal to the power spectral density of the white noise which is applied at the input of the RC filter, that is SW of f. Okay, SW of f into the transfer function of the filter, that is mod of h of f, mod of h of f whole square. Okay, so this is the formula. So what you can substitute is SW of f as N0 by 2. Okay, SW of f will be equal to what? N0 by 2. We know that, right? The power spectral density of the noise is N0 by 2. Then I wrote already what is h of f. That is what? 1 by 1 plus j 2 pi f RC, right? So square of that will be what I can write. So j squared is what? -1, right? So and its magnitude. That is why I have written here N0 by 2 divided by 1 plus 2 pi f RC whole square. Yes, is this clear? Yes, you write this, the square of this one, right? Okay, you'll be getting this equation. Okay, so now I found what is the power spectral density of the noise which is appearing at the output of the RC low pass filter, right? So to find the autocorrelation function, what I need to do, I need to take the inverse Fourier transform of this, right? If I take the inverse Fourier transform of this, I will be getting the autocorrelation function. So that is what is done here. Okay, so to find that, this is the standard form which is given as a reference here. Means if I have Okay. So if I have a function in the form of this, that is e power minus a into tau. Okay. So its Fourier transform will be 2a divided by a square plus 2 pi f whole square. So now I have in this form. Okay. I have a function in this form. So the inverse Fourier transform of that will be, I will be getting in this form, that is e power minus a into tau. Right. Here what is my a value, which is equal to 1 by RC. I can say a is equal to 1 by RC. So with that, I can find out what is the autocorrelation function of the filtered white noise. So which is equal to Rn of tau, right? So which is equal to n naught by 4 RC into e power minus tau by RC. Okay. I think you can have a note of this equation. And how do we draw this one? So this is the power spectral density of the noise, which appears at the output of the RC low pass filter. Okay. And this we call it as a 3 dB bandwidth. So that is maximum is 1 by 2 pi RC, and this side minus side it will be minus 1 by 2 pi RC, and its value is n naught by 4. And when f equal to 0, it has a maximum value of n naught by 2. Okay, and its autocorrelation function can be drawn like this. Okay, so it is what decreasing exponential function, right? So it has a maximum value of how much? N naught by 4 RC when tau equal to 0. Okay, at this point, its value is n naught by 4 RC. Okay, so this is the RC low pass filter circuit. Okay, and this one is the power spectral density of the white noise, which appears at the output of the RC low pass filter, and this one is the autocorrelation function. Yes, is this clear? I said I have a function in this form, right? Something 2a by a square plus 2 pi f whole square. My a is what? 1 by RC, I said. If I take the inverse Fourier transform of that, I will be getting in this form. That is e power minus a into tau. What is a? A is my 1 by RC. So with respect to that, I can write the autocorrelation function as n naught by 4 RC into e power minus tau by RC. Okay, so here at tau equal to 0, okay, for time tau equal to 0, we say the decorrelation, okay, for which the value of Rn of tau drops to 1%. Say of its maximum value is what? N naught by 4 RC, okay, which is equal to what? 4.161 RC. So if the noise appearing at the filter output is sampled at a rate which is equal to or less than 0.217 by RC, okay, samples per second, then the resulting samples are uncorrelated. Okay, the resulting samples are uncorrelated, and since they are Gaussian and they are statistically independent, we say. Yeah, just I took this for understanding, means I wanted to say how do we find the Fourier transform of this exponential. Okay, so this is a decreasing exponential. No? So we can express g of t is e power minus 8 into u of t. So by using that Fourier transform formula, standard formula, we can get it as 1 by a plus j2 pi f. Okay, so this is for one-sided both the things. I think, yeah, this is what we have our autocorrelation function of a noise, right? Our autocorrelation function of a white noise is looks like this. So keeping this in mind, only the value of maximum value is not 1, it is n naught by 4 RC, right? So with respect to that, we can express like this. So for that, so this is what we write, the Fourier transform, and we get this equation. Okay. So instead of referring so much, I took as the standard equation. Okay, so this is the Fourier transform pair what we have shown there. Okay, so fine. I think this is all just I took for making people understand. It is fine. I think this example I will skip. That is about the autocorrelation function. Next definition, one more important definition is the noise equivalent bandwidth. Okay, so just now we have discussed two examples, right? Just I will summarize what we have discussed from example 1 and what we have found in example 2, right? So in example 1, what we have observed, anyone can say? We observed that the source of white noise having a zero mean and a power spectral density of N0 by 2 is connected across the input of an ideal low pass filter, right? Having a bandwidth B and a pass band gain of 1, right? So we found that the average output noise power, okay, will be equal to what? N0 B. Is this point is clear? From the example 1, right? Ideal low pass filter. We found what is the autocorrelation function. No? So we found that its value is N0 B, right? So the average output noise power. See, output noise power is the available power, right? So which is equal to N0 B we found. Then from the example 2, what we observed is a noise source is connected to the input of the RC low pass filter, right? Having a zero mean and a power spectral density of N0 by 2. And we found that the average output noise power, which is equal to what? N0 by 4 RC, right? That is from the autocorrelation function, right? When tau equal to 0, we could find that it is N0 by 4 RC. So that is the average output noise power. And the off power or 3 dB bandwidth is equal to what? 1 by 2 pi RC, right? That is the 3 dB bandwidth. So with respect to that, what we can say is the average output noise power of the filter is proportional to the bandwidth. So this is a very, very important point to be noted. What I said, the average output noise power of the filter is proportional to the bandwidth. Because in both the examples, what we observed is the average output noise power is proportional to bandwidth, right? Because it is N0 into B in the first case. And in the second case, it is N0 divided by 4 RC, right? And here, as I said, the bandwidth will be, in the second case, is the what? That 3 dB bandwidth will be equal to 1 by 2 pi RC, right? So, to make this statement generalize, right, means include all kinds of low pass filters. So, we can define the noise equivalent bandwidth. Okay. To make this statement, generalized statement, to include all kinds of low pass filters, we define the noise equivalent bandwidth. So let us consider a source of white noise of zero mean and a power spectral density of N0 by 2, which is connected to the input of the arbitrary low pass filter, okay, having a transfer function h of f. So we can write the expression for the average output noise power as this one. So N out is equal to, that is the average output noise power, which is equal to N0 by 2, okay, N0 by 2 into integral from minus to infinity h of f whole square into df. So this h of f is the what? Is the transfer function of the filter, okay. So we integrate over the interval from minus to infinity. Even the value of this may change, right, depending upon the bandwidth of the filter. And this is the transfer function of the filter, h of f whole square into df, right? So here I will make it only for from 0 to infinity. That is only for positive frequencies. That is why it becomes N0 instead of N0 by 2. Okay. So N0 into integral from 0 to infinity h of f square into df. Yes, this point is clear. Average output noise power for arbitrary low pass filter can be defined as N0 by 2 integral from minus to infinity h of f is the transfer function of the filter, the square into df. Here I have taken for only positive frequencies. That is why I wrote it is n naught to 0 to infinity integral. Then this h of f square into df, right? So if I consider the same source of white noise, okay, same source of white noise, what I am trying to say here is, which is connected to the input of an ideal low pass filter, okay, having zero frequency response. So zero frequency response we denote h of 0 and a bandwidth of b, okay. Then in that case, the average output noise power will be written as this one, n out is equal to, that is the average output noise power, that is equal to n naught b into s square of 0. Okay, so let me highlight this. So n out is equal to, that is the average output noise power will be equal to what? We can write it as n naught into b, n naught b into s square of 0. Okay. So ideal low pass filter having zero frequency response, which is denoted as h of 0. And a bandwidth we said b, right? In that case, what is the average output noise power? Okay, so I can equate this equation with the above equation, that is with respect to this one, right? To find the or define the what is noise equivalent bandwidth, right? So therefore, equating this average output noise power to that of this equation, we may define the noise equivalent bandwidth, right? So if I equate it, what I will get, n naught will get cancelled, right? So I can define b is equal to what I can say. Yes, anyone can say what we can write? If I equate this equation with respect to this equation, see this n naught will get cancelled, right? So b is equal to, I can say integral from 0 to infinity, right? H of f square into df divided by s square of 0 I will get. So that is the definition of the noise equivalent bandwidth. So that is what is written in the next slide. So equating this average output noise power, right? So we can define what is noise equivalent bandwidth, which is equal to what? Integral from 0 to infinity h of f square into df divided by s square of 0. Okay. So this is the definition of noise equivalent bandwidth. And this is a graph of that. So h of f, okay, minus square versus f. Fine. So frequency here it is a, its bandwidth is limited to minus b to b. Okay. So maximum value is square of 0. So yeah, I hope you should be able to understand this equation. The noise equivalent bandwidth is the what? It is a ratio of integral of the transfer function of the filter, whatever the filter we consider, to the transfer function of the filter having f equal to 0. Okay, that is what is s square of 0 is. Yes, is this clear? Noise equivalent bandwidth. I'm asking you people only, is this clear? The definition of noise equivalent bandwidth. So I started with the previous equation, right? As I said, the average output noise power will be defined like this. That is n naught by 2 integral from minus to infinity h of f square into df, right? Next time what I did, I took only for positive frequencies. That is why I written it is n naught into 0 to infinity h of f square into df, right? So if we consider an ideal low pass filter having zero frequency response and a bandwidth of b, then the average output noise power will be written as n out is equal to n naught b s square of 0. Okay. So I can equate these two equations. I can define what is the noise equivalent bandwidth. So when I have equated these two, then n naught will get cancelled. So b will be equal to this one, integral 0 to infinity h of f square into df divided by s square of 0. So that is the definition of the noise equivalent bandwidth. And this is the graph. Okay. Okay, so far whatever we have discussed is for the low pass filter, right? How do we define the noise equivalent bandwidth and other things. So then same way we can define the noise equivalent bandwidth for the band pass filter also. Okay, so let us see that in the next class, I feel. Okay.